Hello, welcome to the Athena Seminar Series. Today we have Zehao Wang presenting and Tingjun Chen will be introducing.
Okay, yeah, I'll just briefly Zehao. So Zehao's been with our group since the very beginning, starting fall 21, and he's been doing a lot of work in the space of optical networks, especially on optimizing optical physical layer transmission performance, and then how the static of physical layer infrastructure support higher layer networks and applications. And then I think today he's going to talk about some of the work that we've been working on over the past, I'd say, 4 years. And how do we actually expand these to support even heterogeneous services, classical quantum communication in the future. So things are get started.
Yeah, thanks for the introduction. And my name is Zehao. I'm from Duke University, and today I'll present the next generation machine learning driven high-speed optical network with a quantum and sensing service. Okay, so today we have a lot of online applications such as the cloud computing, the streaming, the 5G wireless service, and also the large language model. And all those services require a backbone of the internet, where we have the short connection between the data center and we have the long haul connection between cities and even nations. And the chance of the network is to how to hide that.
Drag it to the right. Yeah, what happens to
More.
There's a high floating medium.
How about this? Click. No. That's
Okay, no, sorry.
and I can continue.
Just click on more. And then click on more on the top. There's a high floating medium.
Oh,
and then X this,
which
that's the participants. Yeah. Share your slides.
And you can click my screen on the top. To the left, to the left.
The left.
Okay.
sounds good. Yeah, so the chance of the network connection now is moving from the copper cable to the optical cable because the optic has the higher bandwidth. So for example, it can easily go to terabits per second, and it can go to very long, such as about like 100 kilometers, where the copper cable is usually like very limited data rate and also inside the short range. And also the optical cable is very low cost because it's using the glass compared to the copper cable, which is using copper. So if we take a look at the picture, we can see that the optical network is connecting between the cities, states, nations, and also inside the data center and even on the chips. So today people are talking about like connecting chips using the optical connection because it's high throughput. Yeah, so but still, it still takes a lot of money to get this optical network infrastructure development. So for example, for a submarine cable, it takes 250 million to 400 million per cable to make it under the ocean. And the goal of the engineers are to increase the transmission speeds under the same infrastructure. And to achieve this, people usually do is to put multi-wavelengths on the single fiber. So we take a look at the wavelength spectrum on the right, and we can see that usually the wavelength transmitting in the fiber is inside the conventional band. And if we are transmitting like multiple signal under the multiple wavelengths, then we can transmitting like more and more data in the single fiber. And besides the high capacity of the data transmission, the optical network will also be enable the other service. For example, people are talking about the distributed fiber sensing where it turns those data transmission fiber into a distributed cable to do the traffic monitoring and also the earthquake detection. And also those existing optical network are used for the quantum transmission, for example, such as the secure information delivery and also the distributed quantum system. And for the next generation optical network, we have our high capacity mesh network in the middle, which it can deliver like high data rate to different nodes or sites. And it can also have the sensing capability for the geophysics measurement and also for the city traffic monitoring. And on the other side, the network is not only carries data transmission, but it can also do, like, for example, the quantum communication and also the wireless service. Yeah, as we mentioned that when we want to achieve the high capacity, we do is carry multiple wavelengths into the single fiber, but this will also cause a problem. The key problem it causes is that when we are transmitting multiple wavelengths, we have the multi-wavelength interference, and the interference can come up like from many devices. For example, it can come from the optical amplifier, where there will be the AC noise and also the wavelength dependent gain. It can come from the optical fiber, where the signal can suffer from the nonlinearity and also some SRS effect. And it can also come from the other devices such as the transceiver noise or the wavelength with filtering effect. And all those interference, finally, they will affect is what we call the quality of transmission, where it will impact for different wavelengths. It will alternately have the different signal to noise ratio there. And the different signal to ratio will lead to different selection of our coding scheme, and it will impact the link throughput. So for example, if we have the higher SNR, we can select like 64 QAM, which can take your more data rate. And if the SNR drop, we can only select like 16 QAM, which gives like lower data rate. Yeah. And what do people do with different kind of network? So for the university and home network, because it is less of the traffic, usually people do is they transmit single wavelengths and single fiber. And for the submarine system, on the contrary, because it is so expensive and the data requirement is so heavy, that usually people do is 4-channel loading, that they load all the wavelengths into the fiber. And for the commercial mesh network is something that in between that they have the data traffic, but it will not take all the channels. So usually they do a partial channel loading, like with some channel loaded with the data traffic and other channel that without the data traffic. And for some companies such as Google, what they did is for those unloaded channels, they put optical wideband source to emulate those data transmission. And for some other companies, they are doing the partial loaded, where they just don't load those signals. And if there's a new data requirement, then they just add a new wavelength into that fiber. But however, as we mentioned, that there's like between the wavelengths interference. So adding a new fiber, new wavelength, it will affect the existing signal, and it usually takes like minutes and even hours to add those new wavelengths. Yeah, so today's optical network is more like a static optical network. So the wavelengths running on the optical network is usually as what is planned. And there's usually no like traffic balancing like between the different routes. And if there's like a new traffic demands come up, then usually on the physical layer, it's very hard to handling those new requests. So we are proposing to a more like a dynamic optical network where on the physical layer, we can easily add and drop the wavelengths on the arbitrary link using the machine learning enabled quick network reconfiguration. So this kind of the reconfiguration always need we to have accurate provision of the quality of transmission on like arbitrary link. And the essential part is about the optical amplifier because that's the most where the noise optical noise comes from. So for the optical network component, so we have the reconfigurable optical add and drop multiplexer called the RODEM. So this kind of device can add and drop arbitrary wavelengths to a node. And the other part is called the urban doped fiber amplifier, or called EDFA. And this is what the problem come from. So if we put a flat input spectrum to the amplifier, then actually its output power, we can see it has a shaped gain profile that for each of the wavelengths, the gain is like different to each other because of the optical nonlinearity and also in turn wavelength interference. And those gain profile, it depends on many factors, such as the physical devices, the gain settings, the input spectrum, and channel loading. So it depends on so many things that it's very hard to do the modeling of that gain ripple. And what people usually do before is because the internal structure for the amplifier is simple, so people will use like theoretical model to model that. But in the practical system, things are different because the internal structure will be more complex than the theoretical one, and also those physical parameters are very hard to find in the practical system. And also people thinking of using like machine learning to help to do the EDFA modeling, but there's no existing optical data set available. So they just collect their own data and evaluate their proposed model on their data. So there's like missing our open comparison for benchmark. So what we did is we collected open EDFA data set and also help for the machine learning competition among different research groups. So this is the open EDFA gain profile data set we collected using the commercial Lumentum EDFAs and on the Cosmos testbed in the New York City. So basically we collect over like 16 EDFAs with different set of gain ripples, and for each of the gain settings, we measure like 3,000 of different kind of channel loading there. And this data set also was used by the OFC 2026 machine learning challenge. And if we take a look at deeper into the data set, the first thing we can notice is the x-axis is the wavelength and y-axis is the gain ripple. And the different color represent different devices. So the first thing we have noticed is that different devices, they do have different gain ripple. And the second thing is that for different channel loading, for example, the first one is 4 channel loading, and the second one is single channel loading. And for different channel loading, they have different gain ripple. And also for the different EDFA types, such as the booster and the preamplifier EDFA, they also have different different gain ripple conditions. So we will need to go from the data and find the accurate prediction of those gain ripple. And our solution is similar to others that we are using the neural network to do the modeling. And if we take a look at the result, we can see that 77% of our prediction is within the measurement resolution, and 98% of the error is within the 0.2 dB error. So it's quite good result, but remember that it always requires you to make the measurement of 2,600 of measurement on a single devices. So that's a lot of measurement and take a lot of time. So the next question would be like how we can reduce the data measurement requirement to achieve the similar performance. So we use the transfer learning to save the data collection process So if we take a look at the table, we can see that before the training, it takes like around like 2,700 of measurements. And for our transfer learning, we only use like 13 measurements there. And what the performance look like is we take a look at this picture. So the y-axis is our source EDFA devices index, and the x-axis is our target EDFA index. So the diagonal line there would be, we have the our model like training and testing on the same devices, which means there's no like transfer learning. And for example, for there that we have, for example, for the 0.09, that element, it means that it is trained from the first EDFA and transfer to the third EDFA. And we can see basically there's like have similar performance for the gain ripple prediction. And it only requires like 16 measurements for these new devices. So it do save a lot of the data collection time. So now we have the data set. We have quite a current model for different devices. But when they are deployed in the field, then things will still be different and they'll still be difficult because the field have different conditions. So the first condition it is the parameter might change. For example, the fiber banding condition will change the receive optical loss, and also like during the years, due to the aging effect, the device's parameters can also be changed. The second condition is that although those parameters can be changed, but it's very hard to remeasure the device again, because once it deployed in the field, it might be inside the downhole, it might be under the ocean, and you can never get the device back and do the measurement again. The third requirement from the field is usually it's very urgent to launching the service. It usually will not give you so many time to do the measurement, because we always hear of the news that when there's a fiber cut event happen, the service provider are losing like millions of dollars per hour. So that's usually people want to launch the service as fast as possible. And we are targeting as arbitrary network rerouting. So for example, we have the red dash route like connecting the location between A and B. And when the new traffic demand come, we want to have the new green route to have the actual connection between the A and B, and how we can quickly prediction the link condition. So the first target we are looking at is the optical power prediction. We're looking at to predict the signal power for the merchant design. It will help for the merchant design, the hardware protection, and also for the channel flattening. And usually there are two methods for the link prediction. The first one is called the direct cascading, where we have an input spectrum that we put into our first device model, and it will give an output prediction. It will go to the second device model, have the prediction again, and then finally it will get the final output. This does not need you to do any remeasurement, but so you know, like when your device is increasing, then the error would always accumulation. And the second one is to avoid those error accumulation. People usually treat it the whole link as a system and do the end-to-end measurement and do the modeling. But the problem is that when you are switching to a new link, you always need to do a lot of new measurements, and it takes time and delays the launching of the new services. So the key research question there is how we can avoid those bad error accumulation behavior, and also minimize the measurement on a new end-to-end links. So to solve this problem, we are proposing the cascade learning, where we have some pre-trained EDFA gain models, which is most complicated part and the hard to model part in our link. We also have some on-chain span models And then we connect all of them together and using a small amount of the end-to-end measurement to retrain those span models. And we hope this method can adapt the optical link model to avoid the error accumulation. So what does the result looks like? We first take a look at how the direct cascade behaves. So the x-axis is when the model performance passing different number of the EDF phase, and the y-axis is that through arrow. And we can see that the error will gradually accumulated when it passing more and more EDF phase. That's what we expected. And when we come to the end-to-end model, we can see that it always has very good performance on each, like passing through each number of model. But remember, it always needs like a lot of remeasurement on every topology. And for our proposed cascade learning, we can see that it has a similar performance as the end-to-end, but it only needs one additional end-to-end 4-channel loading link measurement. So it saves a lot of data collection on the link condition that, but also have a very good performance there. Okay, so now we have a good solution on the optical power modeling for arbitrary optical link. But the real thing that the service provider wants is the quality of transmission, which determines the coding scheme and also determine your actual optical network throughput. And there was some optical terms like the generalized SNR or optical SNR to evaluate how your quality of transmission is. And that's our actual prediction target. But now we're not only dealing with the signal power, we are also dealing with the noise. And the noise can also be accumulated. So if we take a look at our bottom optical link, we have the transceivers at our left, and those passing through the data switch and go to the amplifier and go to the fiber and finally received by a transceiver. And we can see those noise come from everywhere. It came from the amplifier, which is called AC noise. It can come from fiber, which is the nonlinearity noise. Also, there's transceiver itself and the noise. Again, so with our research question would be like, on any arbitrary link, how we can minimize the measurement, but also achieve a very good link prediction performance. So the solution will also, again, be the cascade learning, but now we need more component model to do the modeling. So we will have like individual like EDFA gain and noise figure model for the signal node and the noise prediction. And we also have the fiber loss and nonlinearity model for signal and noise. And the next step is we connect all these models together as what they are in the optical link. And at the end, we can calculate what's the GL. There. And our final step is we are using a small end-to-end measurement and to retrain those at the and see how it helps the link performance modeling. So the x-axis is the training set size, and the y-axis is the mean absolute error. And if we look at the end-to-end, we can see the typical curve. We can imagine that if it has enough data, it can get very good performance. But if the data if it's only with the limited data, then the error can be very high. And for the component cascading, it's on the other side. So we see that the component cascading is now with something called the parameter refinement. So this is the method people use to like refine some of the parameter of the devices to have a better adaptation onto the link, but usually it's with like very limited adaptation that one can solve from the our result figure. So for example, if we take a look at the purple line, if it's with like zero like end-to-end training set, it has some high error. And we got some new training, it can jump to some certain level, but keep constant over there. So it can adapt to the link a little bit, but not get a very good prediction. And for the cascade learning, we can see that it requires less optical link measurement. And it also get better QoT prediction performance. If we take a look at any of the training set, we can see that the cascade learning method, it always achieve like lower error compared to the others. Okay, so now we have a more dynamic mesh network on this optic network. When there's new traffic demand come, we can quickly predict the new link performance and add those service into the network. But the network is not only about the data transmission, it's also about the sensing capability. For example, people now today they are using some single fiber cable in the European nuclear research project to monitor the temperature, and some other universities such as the Caltech, they are using the fiber to monitor the earthquake. So how does it happen, and what the philosophy there that making the fiber sensing happen? So the first things we need to aware is that when we are transmitting a signal into the fiber, there's always a reflective signal from fiber. And if we take a look at spectrum, we can see the major power reflected is at the same wavelength as our transmitted power, which is called the Rayleigh backscattering. There's also some other scattering like the Brilliant backscattering and also the Raman. But for the major fiber sensing, people are focusing on the Rayleigh backscattering. And those backscatter data, the phase will be affected by the temperature and also the fiber strength. So when we send in a green pulse at the beginning of our time, it can be reflected by the fiber. For example, for the location z equal to 0, then we get the reflect optical signal at the beginning of the time 0. And the signal can travel all to the end of fiber and get this reflect signal back to our receiver. Then it is where it is at some point at the end that the receiver gets some reflect signal back to the fiber end. So this kind of the method, it can convert the location information into the time information. And by looking into this time information, we can recover the temperature and the stream changes using what people call it is the distributed acoustic density. We did some field trials using the DAS devices for different kind of projects. The first project we did is for the New York City traffic monitoring and also for fiber cut events. So we set up the fiber sensing device in the Columbia University, and we are monitor the green routes that the fiber routes all go to the downtown of Manhattan. And the result shows that the x-axis, this is a typical waterfall plot that you can see from the fiber sensing devices, where the x-axis is the location and y-axis is the time. And we can see some like tilt lines like happen near like 2,000 meters. There's some like moving objects that are moving with the time changes. And what we're really looking at is some abnormal signal due to the fiber agitation. where we see those things happen, we can switch our data traffic to some other routes, or the backup routes that we can avoid the link break and also the service break. So that's one of the example. The other example of optical fiber sensing is it can be used for the geophysics detection. So this is another field trial we are doing for the underground layer detection. So the blue dot there what the geo people call the geophone. So this kind of the vibration sensing devices, and usually the geo people did for the past decades is they deployed thousands of these geophones onto the ground over, like, for example, 3 x 3 kilometer area. It takes them 1 week to make the deployment and they collect the data. And after the data collection finish, they take all these geophones back. It takes another like 1 week for them to do so. And for the fiber sensing, we can have some like fiber all go to the underground and sensing the vibration. So we put some downhole seismic wave cells there which generates the vibration, and the vibration can go up and go down and reflected by the bottom of the rock layer, and also then go up again. So looking at the water flow plot where the x-axis is the time and y-axis is the depth, we can see some clearly like the P wave and the S wave, which the geophysics people can use that to calculate what the velocity model of your wave transmitting on the ground to determine like what's the material of your rock, and also like how many layers there will be like on the ground for those geophysics measurements. Yes, so we show that we have the sensing capability for the fiber network, but it's still quite challenging because it's very, as we mentioned, like the fiber cable is still expensive, and if we like assign those service the single fiber to like fiber sensing, it's very expensive. And also we have the other service like quantum wireless. So the question there would be whether we can like make all those servers on a single fiber on different wavelengths that we can run in like multiple servers at the same time on the same infrastructure. And the first field trial we did is like study the coexistence of the fiber sensing, the 400G data transmission, and also the 5G mobile service. So look at the figure. So that's the launching spectrum there, where the x-axis is wavelength and y-axis is power. So we can see the DAS, the distributed acoustic sensing, the analog radio fiber running the 5G signal, and also the 400G link. This is our experimental setup. So it's a little bit complicated, but if we break it down, so the first part is our 400G link. So it's passing some data switch, the transmitter, the receiver, but eventually this red line and the box here is 400G data link. And the second part is our 5G new radio signal, where it go to the fiber, detect by the receiver, go to the air, and finally analyzed by the receiver. And we also have a part for the fiber sensing. And we put these three signals together. We want to see whether they will have impact on each other. So this is one of the results we have there. So it started between the impact between the 400G and also the fiber sensing, where the x-axis is launching power of the DAS, and we have two of the DAS nodes. The orange one is pulse-based DAS, and the blue one is constant amplitude DAS. The y-axis is called the prefect BR, so it's kind of the metric to evaluate the 400G signal quality, where the red line there will be when the 400 links breaks. So from this graph, we can tell that for the pulse-based DAS, its optimal operation range is conflict with the 400G signal, but for the constant amplitude fiber sensing, the two signal will work fine. Only when we increase the DAS power to be a very high level, we see the 400 link breaks. And on the right figure, this is the waterfall plot we have where the x-axis is the location and y-axis is the time. And we are using the fiber sensing to monitor those fiber annotation, and when we got those signal, we can switch our fiber link to some new route to avoid the service of breakdown. And we can also see from fiber sensing when the fiber is breakdown, the later part, the signal pattern will be very different. Another field trial we did is to study those data traffic signal with the quantum field. So we have our 400G and radio signal at the Wilkinson building, and we are transmitting those signal through our fiber into the transfer field where the quantum center it is. And at there, they are mapped with the Ti-92 ion trigger, the quantum photon, where those signals can co-propagate through different fiber, and then the quantum photon will go to detected by the single photon receiver, and for those classical traffic, it will go back to a Wilkinson building and demodulate and decoding there. And this is the result to show the performance. So if we first take a look at the bottom three figures, so the x-axis is the launching power of the 400G and the analog radio fiber signal, where the green one is the coherent 400G, where the red circle means that the link is breakdown. And on the right side, the red axis is EBM, that's the evaluation metric for the 5G radio fiber link, where the black dashed line means it's the threshold. So above that threshold also means that the link breakdown. So using the figure, we can tell like under those links what the safe range for those two signals. And we are testing through a passive fiber, which is 25 meter, a Bedouin loop field fiber, which is 2.8 kilometer, and also a fiber spool of 10 kilometer. And what we actually looking at is how those classical signal impact on the quantum. So that's where the blue curve on the upper three figure it comes. So basically that's like we are running the clock signal and we open the single photon receiver, and we counting the photon that link from the classical traffic into the Ti-92 photon. And if the photon count become higher, it means that there are too many impacts from the classical channel that we are like downgrade your quantum fidelity. So what quantum people care about is what they call 1% of the fidelity drop. That's what we have aligned on the right, that's the threshold when the quantum signal drop like 1% of their quantum fidelity. And on the left is only like 0.2% or 0.5% drops. So given this threshold, we can give them the safe range where we are running these three different kind of surveys. What the safe range to make three signal co-propagates on the single fiber. So for the conclusion, so we have a high capacity and high dynamic optical network enabled by machine learning to have like dynamically traffic balancing, and also the high accurate provision on any abusive link on the fiber network. And we also have make the optical network not only for the data transmission, but also for the sensing, for like geophysics measurement, and also for the traffic monitoring. And finally, we studied how those different services can be coexistence on the same network, and we do not need to deploy new fibers in our area. So we studied like how the quantum fiber sensing, the wireless service, and the data traffic coexist there. Yep, that will be all my presentation. Thank you, and please let me know if you have any questions.
in for the pump network. Then for using GPP, UDP, or they're just occupying the section of the optical space.
Oh, yeah, it's a good question. So there's no, there's no like higher layer protocol for the quantum transmission. Basically what they did is they're sending some single photon. So, like single photon, you cannot have like too much protocol on single photon because it only carry very limited information. And when they are sending the single photon to the link, they're detecting single photon condition, and it's more like secure information delivery on the single photon. Yeah, and it's not drawn in this spectrum diagram because the single photon is outside the conventional 50-50 nanometer wavelength is at the time M2. So the spectrum is too far, so we did not draw that photon signal into the link. Any other questions?
Also, like you have, you went through, 5G traffic, you went through the quantum application, you went into the traditional fiber application. What kind of application did you, for example, LN inference traffic? Do you think it is possible that we could include that as part of the application for the optical network?
Yeah, so it's a good question. Actually, I think for example, so usually between our data traffic that the data transmission we put in our experiment is 400G transmission, which is 400 gigabits per second running over the Ethernet. So it's quite very high bandwidth, and give a sense of what Duke today is running. So Duke is running around 10 to 40 gigabytes bits per second running on the fiber. So it's much higher than what is usually people do for the running, and it's not only for interference, but you can also take them as like the training data, the large training data transmission between the data center can also be supported by this kind of service. So it's much higher capacity compared to like what we are daily uses for our like service such as streaming the game or the LLM interference.
Any other questions? Thank you.
Yeah, thanks.